Fine.
By cutting down the number of edges you check first. Basically, you just narrow down the amount of edges you check and first.
So I was just correct then.
Because
Because I said it was inserted initially.
Well, yeah, I agree with you, but I was like, if you have the edges, and there's not being as much as you have no edges.
Got it, okay.
I get what you're saying.
And it's a last question, and then one of the responses like using the infinite series, it's like when you don't have much capacity for infinite series. I shouldn't say it's.
I don't have enough capacity for Sigma, bro.
So now in graphics programming, we are studying things like generating images that takes camera into account, that takes model into account and mirrors and do ray tracing. First ray tracing very slowly in your CPU one by one, but the mirror might hit the, but a ray coming from the UI to the pixel hits a mirror and bounce. Now, you need a bit of geometry to compute what's the direction of the bounce, or vector, of course. But then if it bounces, it might hit the sphere. If it might hit the sphere, then the illumination of the sphere, depending on where is the sun in the image, and what is the orientation of the normal to the sphere versus the sun, and then you might recurse between the mirror and another mirror that you see here behind you. So there is a matter of depth of recursion of the ray tracing. So, like, makes the ray bounce once from the mirror, makes them now bounce from the mirror behind the camera, makes them bounce once again and once again, or in a bit. I have these videos in much higher quality. I just didn't prepare for you for the interrupt, but just taking a few billboards, put the picture of the cat on each billboard, and I then change the camera direction and the camera location. So if you are changing the camera orientation, then these two billboards are changing, and the orientation of these billboards is, they're not orthogonal to the viewer perspective. That's why they look twisted. So that would be, in this case, there was one more relatively nice one. The resolution can go up or down, but here you see a sphere that is a mirror sphere next to a few spheres that are opaque, each one with its color, and there is some background over here, and the camera is moving, and we will do it first in excruciating slowness by just using our CPU, just one line, or a small number of CPUs only, and then we'll expedite everything by moving to fragment programming and do it in on our shaders programming GPU-wise. So it's, I think that it's fun course. There was already a request to postpone homework 3 to Thursday, which is, fine. Question about homework 3?
It's not really homework 3, but I'm kind of confused how you deal with the local feature size requirement when you have the medial axis going like infinitely close to the border of a shape. Like you showed us an example of a rectangle where the medial axis is like next to the vertices, right?
Yeah, so there is a point where its local feature size is 0, of course. So which, if you check the graphic literature, like the main conference in graphics is without a doubt called SIG-graph. And if you check the graphic literature and look for sharp edges, shape reconstruction, that's always a much harder task. Everything that is non-smooth is, it's big topics that I don't discuss here, but it's never easy because you are quite likely not to have, if that's a sharp corner of my object, then unless I have infinitely many points, it's pretty hard to get this corner exactly. So we actually, with Josh and Kobos, we had and people from the mining department, not data mining, mining, shovel mining, nice work about try to predict landslides out of cracks, which involved segmentation, which involved data from LiDAR, and exactly the sharp edges in 3D. The ridges are exactly what you want to catch, but that's exactly where getting it from just 3D points, even with colors, with RGB, XYZ, was very tricky and interesting. Okay, some other questions? Summarizing about a quad-tree balanced balanced quad-trees, which is, remember, definition of balanced quad-trees, every two nodes, every two squares that touch each other, either they share an edge, either have the same size, or one is twice the size of the one that is neighborhood. And neighborhoods are just defined based on, neighborhoods are defined by edges only, not by diagonals. And we said that if we have a quad-tree tree that has m nodes, and n here is not under your control, it's depending on the data. You have shapes, you want to build the quad-tree until every square of the quad-tree is either fully inside your shape or outside your shape, or every cell has only one vertex or aligned with the edges or whatever the input is. And sure, assume that the input has integer coordinates, so it's not infinitely narrowed, but you stop your splitting at some point. But you ended up with a quad tree with n nodes. So a balanced quad tree, which are we creating? We are taking the original quad tree and start splitting nodes once needed. And I wave some details here about how do I always pick the nodes just near me. It's not hard, just not that interesting, and not how to find out yourself. How do I find a node near me? If the node near me is too large, we had this algorithm last time, is more than twice my size, then the node, my neighbor needs to be split. And maybe needs to be split again, and needs to be split again. What did we study? That if the original quad tree had m nodes, then your new then the construction time would be order of the, d here is the height of the tree. It's what we use h to, now it will be d for the depth, how high is the tree times the number of nodes, and why this order? Because we said that the balanced quad tree is similar in terms of complexity to the original quad tree. As long as 37 is your favorite, you consider as small enough constant, then the original quad tree, then the balanced quad tree has at most 37 times more nodes than the original one. Okay, and that's the time to build it. Okay, and and if we have a balanced quad tree in general, we just balanced or unbalanced, we can always create a mesh of triangles out of the quads in the quite obvious way. Here is one square of the mesh. Look at the two diagonals. That will create triangles of 45 degrees. If you don't like them, make them of a 90, 45, and so on. And that would be your triangles that you create after a quad if you don't like the quads by themselves. Okay. I want to take a very brief break from quad trees, or trees in general, and to ask you, we'll talk more about linear programming, and we'll mention convex programming in this context. But in general, as you probably know, convex optimization is an extremely important topic used all over the place, and convex optimization is much simpler, much easier than non-convex optimization. And my question to you is why? Yeah.
Is it because, like, in the shape on the right, you have like a local minimum, so if you reach that, you might think that's the goal, even though it's not?
In convex, in both sets, if I'm trying to minimize something, I can find a point, I can look at the neighborhood of the points, and if just local improvement doesn't help me improve my cost function, I'll call it a local minima. But it's very hard to know if my minima that I'm in is a local minima, which in convex programming it's unique and well defined, while in the non-convex programming it could be one out of exponentially many local minima, which is roughly an explanation of why NP-hard makes it slow to hard. But the reason that I'm telling you all of it now in the middle of quad trees is because I wanted to tell you about Fabio, our new puppy. That was over the weekend. So that's Fabio, about 7-8 months by now. He was in his crate, looking at me extremely sad, begging me to let him out, kind of whining. I was trying to play with the laser pointers that he really likes. He's crazy about it, so he was pushing the crate hard. I put treats outside the crate, trying to understand his reaction, so he kept looking at me with this heartbreaking look. And I'm telling you about it because the gate was open all the time. He was stuck in a local minima, while he was trying to get outside while I stay close the crate. So, yeah, don't get locally minima. Okay, we are back to quad trees. We are done with balanced quad trees and switching to compressed quad trees. So there is an elephant in the room all this time, that the height of the quad tree doesn't depend on how many data items you have. It's depending on how many data items, but also about what is how close they are to each other. And this height can be arbitrary, and it can really mean that for you just have 2 data items as checked in the homework, but the height is 50, 60, 70, typical height for quad trees. So let's combat it by talking about compressed quad trees. So to talk about compressed quad trees, let's first make a lemma about a family that has lots of children. It's my terminology about a family blessed, but I want more markers. So not good. Okay. So a tree. And in this tree, you see 2 leaves. So my terminology, M is 2, the number of leaves is 2, while the number of internal nodes in this tree could be, is in this case 1, 2, 3, 4, 5, 6, and there is no correlation between it. It could be a tree with very few leaves, but a lot of internal nodes. So F here, F is 6 in this example, and M is 2. But now I ask you, what if my tree has this property that every internal node has at least 2 children? Or every node is either a leaf, but if it's not a leaf, it must have 2 children at least, maybe more. So this will not qualify as a tree that satisfies this family blessing thing. If I want to satisfy it, then I can do this part, and now my tree is fine. And maybe, yeah, and you see this guy has 3 children. So I want to prove to you that in every such tree with this property, that every node either has 0 or at least 2 children, in every such property, the number of leaves is larger or equal than the number of internal nodes. It's -1 over here. So, yeah.
Is this because it's like a binary tree, so it's like the number of leaves is like 2 to the h?
So what I had there originally was a perfectly good binary tree, but I had a lot of nodes that has only 1 child, right? So it's binary, it's like a stronger binary of the binary trees, that it's really no less than 2. So
In other words, is it like you have more children than parents?
yeah, you have more children than ancestors all the
Yeah.
way, yeah. So it's not only the parent, yeah, I guess that's it, your intuition. It's, so I'm not only bounding the number of immediate parents, it's parents, parents of parents, all the way to the, yeah. So let's prove it. That's, I can always pick one of the nodes and call it the root. And once I pick the root, I can hold it back in the air, and then all the nodes, gravity will pull it down. So I'll have the root all the way and all the way down, doesn't matter. So this does not satisfy my condition, because that's the only leaf, that's the root, that's the only leaf. That satisfies my condition. It has 2 children, 1 leaf. So this is the best case. Let's even check one more case: 3 leaves, only 1 internal node, and so on. So by induction, let's assume that it holds for each and every tree in the world that has less than m leaves, less or equal than m-1, strictly less than m leaves. M is now, M will be maybe 4, if this is my example. I still didn't see any tree with M leaves, but I've seen tree with 3 leaves or less. That's on the whiteboard. And now it's the first time where I see a tree like so that satisfies my condition. It has now 4 leaves. No, it doesn't. It has 3. So here we'll have, now it has 1, 2, 3, 4 leaves. Now I'm happy. Okay, but remember, for any tree with less than 4 leaves, it's already proven. And that satisfies my condition, of course, yeah.
Does the condition, right, is that every internal node has at least 2 children, right? And then this one, like the left node only has 1.
The left one?
No, the right tree with the leftmost child
that
on
one
the
is
second
not.
row.
Nope.
Go up to.
Sorry.
This one is,
One more.
oh yeah.
There, yeah.
Yeah.
Oh yeah, so I skipped the case of 4, but the induction is still fine. Just I didn't create the example of 4. So let's get to 5. Let's assume that I proved it for every tree that has exactly 4 leaves and the lemma is true. And now I'm in the case of, let's prove it for 3 of 5 by induction. So I see 2 leaves here. Actually, if this guy had, let's talk about, how did I call it? Let's talk about P over here. Everybody's good with this green, or should I bring more markers? Let me know if, yeah. So P has 2 children over here. If P has more than, let's say, 5 children, then we can remove 1, decrease M, without changing the number of internal nodes. So it's even stronger. So let's assume that P has exactly 2 children. And now what do? I remove both these children from the tree together with their parents, together with the edge connecting them. So what did I get after removing this case? It's K and I removed all of them. It could have been that I just get rid until I have exactly 2, both fine. Let T prime be this 3 after I removed it. So this 3 after I removed these 2 guys, it has, since my original tree had M leaves, now I have less. How many leaves do I have? If I have M leaves, if I had M leaves, let's think about it. It's, I deleted these 2 leaves, but in return, P itself became a leaf by its own. So I got M minus 1 leaves. So in this tree, F prime, the number of leaves that I have in this guy, is smaller or equal than M minus 1, which is the original part. But what about F prime? What is the relationship between F, the number of leaves, in the original one, versus F? So P that used to be internal, is now a leaf. So F prime is F minus 1. So if F minus 1 is smaller or equal than M minus 1, then add 1 in both cases, and F smaller than M. And actually you can prove that there is a bound of 1 here, but that's fine for our purposes. Everybody is good? Everybody understand what the lemma tries to say? And now I'm looking at the quad tree that I created. We are done with the compressed quad tree. Could be the compressed, but it could be the it could be the balance. Doesn't have to be. But I'm looking at a quad tree that is built on a set of items, set of points. Say. And I noticed that that something funny happens in this case. This might or might not be the root of the tree, doesn't have to be. And this might be a leaf or not, doesn't have to be. But I'll call this whole set of nodes a thread if, and I'll call this set of nodes a thread if this node points to this one, points to this one, points to this one, all the way until this one. And all the thread, each one excluding the last and excluding the first. So everything else, consider every such node has exactly 1 child. So I'm looking at the whole, quad tree, and notice that the root has 2 children, but then this child has only 1 child, 1 child, 1 child, and now this guy has already 2 children or more. I mean, or it might be children, it has all the children, but all 4 children, but some are empty, doesn't have any data points in them, except empty leaves are fine. And I want to compress it. See that there is too many nodes that don't help me in any way in the memory, because so far the bound that I can have for the tree before it was if it has M data points before the compression, then and D is a height, then the number of nodes might be D times M, the total number of nodes. Right? Every node, or every couple of points, might cause the long thread that is the whole height of the tree. D is the height of the tree. It could be that, well, one node it's a bit hard, but two nodes it's very easy to put them very close to each other. Hopefully you all did it in the homework. And the key in your quad tree keep splitting and splitting and splitting, trying desperately to separate these two nodes, creating an unbounded length stretch. And now I see so in my quad tree altogether, I see one thread, and maybe I see yet another thread. Maybe I see another thread over here. Remember, what is a thread? A set of nodes, each one has only one child, and it forms a chain. Now, there is an advantage of keeping the quad tree in its current shape, and that's one, simplicity. And B, that, remember, nodes don't need to store what is R of V, what is the region that are corresponding to. Based on the path that leads to the node, I know exactly what is the region that a node corresponds to. Right? We talked about it last time. Go to, if I know that a quad tree starts between 0 and 7, then the left subtree of the root would be between 0 and 3, 4, and 7, and so on. So based on the path to a node, I know what this node corresponds to. So there is an advantage of storing the tree in this way, but there is also a lot of waste in the case that the input is very small, but the tree is very high. For every node or pair of nodes, I'm still storing a very tall thread. So what should I do when I see such a thread? I mean, I see it after building the tree. Look at this node P, that one of its cells, one of its 4 cells, points to the beginning of such a thread. Why don't we instead making this cell points directly to V? Makes sense? Every time that I see a thread in the tree, if I want to compress it, then instead of this pointer points to this guy, I'll tell it, hey, you are actually pointing to this guy directly. Now, V now has to store its range because there is no left right. Here, just for, because I cut and paste when I prepare this slide, and I always keep exit from cell 0, but it could be any of the 4 cells in each one of them. So I don't know where these cells are going to. So V needs to keep its region. Okay, so it will keep the leftmost upper right, the lower left upper right points inside V. And I need to keep a flag that tells me if it's normal cell or cell of this special type after the compression. But I can prove something about this tree. Yeah?
You have multiple threads starting from the same root?
No, because then the root has degree 2. So the thread starts at either the root or start at a node that has only, sorry, the thread always starts from a node that has only one child and ends at a node that has only one child. Or no children at all, and then it's a leaf. But if it had only one child that is non-leaf, good question. If it had only one child over here and it's not a leaf, then I could have keep this pointer points a bit lower. I could have skipped this guy also, yeah.
Would you ever have one child, or a splitting policy not allow for one child to be that low?
So, no, it's the thread is defined when I have one child. The split, yeah.
But it needs to terminate at 2, at least, correct?
at 2 or at a leaf. I mean, it could be that I'm jumping all the way to the leaf directly. And the leaf might have whatever you want. You want to keep one data point in the leaf, fine. You want to keep 17, fine. I don't care. It doesn't affect. All I want to say is that now, how many internal nodes will I have in the tree? Right? I had the bound beforehand of d times m, the number of, it's n in the slide. And n. So before that I had this annoying d over here that was quite unbounded. What happened now when the quad tree is compressed? When the quad tree is compressed, how many leaves does it has? Every known empty leaf must contain a data point, and you only have n data points. Every internal node has at least 2 children, because otherwise they would have jumped over it, would have compressed it. And then if I want to store also empty leaves, then it means that for a node, it has at least 2 live one. This one should be live, and maybe I have 2 more empty leaves, but at most 4 leaves, and that's a very, very pessimistic bound of the number of leaves that are empty. They should be only on live nodes altogether. So what did they get by the compression? That now every internal node has degree which is 2 or more. So I can apply the lemma that we just saw about the family blessed lemma. So the number of internal nodes is linear in the number of leaves. So all in all, you have n data points. You just have n leaves. You just have n nodes altogether.
What's that last line though? That's not. Where did that last line come from? Is that the lemma? The lemma?
No. It's to say how I didn't. Some leaves are empty, don't have data points.
Oh.
But why? Because let's talk about this case. Terrible. Let's talk about this case. So I have 2 data points. So yeah, I have 2 data points. My splitting policy is every leaf should contain at most 1. So I split, I create 1 live with data points, 1 live with data points, empty and empty. But these 2 empties are charged alike because of 2 non-empty ones. Okay, so for every, the parent has at least 1 child.
Okay.
And it's actually less than 4, it's much smaller than that. Now, so the tree star, so we still enjoy most of the properties, the simplicity of quad trees that fast to implement, but pretty much now the memory is linear in the input. You don't get this factor 60 because that's the height of the tree. Out of the blue. It unfortunately by itself does not imply that the search would be only log n. If we want logarithmic search, we need quite a few more trees. But it will at least says your memory is completely manageable. There is no factor of 60, and you enjoy everything in the pattern. So just to summarize complexity of quad trees, if you have n data points, what is actually the height of the tree? Let's ask when I define it now, a bit more general term. Let's ask what is the maximum distance between any 2 points, the diameter of the set. Let's ask what is the distance between the 2 closest points, and the height of the tree is log of this number, log 2, right? I start with this distance, split by half, split by half, split by half, and when the cell size is less than d min, the distance between the two smallest point, then my next split will finally separate them. Make sense to everybody? Once again, that's log 2 of maximum distance versus how many iterations of halving do you need until you finally separate the two nearest points. So that's without any assumption about integer coordinates. And so this is D if you don't compress it. If you do compress, you're down to order n many nodes. And we are done with quad trees. And our next data structure will take much less time to describe. It's probably more useful, more general, more useful in many geometric databases, game design, robotics, and so on. Very, very general. It comes up with not too much theory, but it works. So I have a set of objects. It could be points. It can be segments. It can be in 2D, 3D, any dimension, whatever. And I want to tell you about R trees. So, I think that I'll go to. You have some shape. I'll go to look for markers in a sec. I look at a shape, I look at min x, leftmost point, max x, rightmost point, lowermost, highermost. That would be the bounding box. So it's very easy to find bounding box of shapes. And bounding box here stands for axis parallel bounding boxes. Sides that are parallel to the x-coordinate, to the x-axis or y or z, etc. So I want to tell you what would be an R tree for this data set. So to start with, here are my items, and I'm going to put bounding box around them on each individual item. So I put bounding box on each item individually. And now I decide for some items I want to merge them into a pair. I decided that 8 and 7 looks like a nice pair, so I'll merge them. So shape 8, all the shapes, all the bounding box of the original shape, these correspond to level 1 of the tree. Convenience is the tree is upside down. The leaves corresponds to the individual shapes, and I'm going to build the R tree from the leaves all the way to the root. Except that now it's from the leaves all the way down to the root. So 1 here refers to item 1, I'll keep its bounding box. 2 refers to item 2, keep their bounding box, and so on. So at the leaves you have bounding boxes together with who are the individual items that corresponds to this bounding box. And now I decided that 7 and 8 should be merged, should be paired. So I'll pair them, and what I'll store as a common parent in the tree is bounding box of the union of 7 and 8. How do I do the union of two bounding boxes? Trivial. Here are two bounding boxes. Look at the minimum of their two x's. Minimum of the two x's is a new x coordinate. Maximum of the two x's, min y, max y. That's the bounding box of the two boxes. So that's what I'll store. It's a common parent of 7 and 8. Similarly, I'll decide that 6 and 5 are merged. Look at their bounding box. That's this node over here. And at the internal node, you don't keep the individual items. You're just keeping the bounding boxes. So this node keeps the bounding box, namely x min, y min, x max, y max, of this yellow bounding box of its children, 5 and 6. Similarly, bounding box of 3 and 4. Similarly, bounding box of 1 and 2. How do I decide to which one to merge? That, of course, $1 million question. That's
Nearest.
what defines what.
Nearest.
For points, picking nearest makes perfect sense. For shapes that are a bit more complicated, then the distance doesn't necessarily well define, and yeah, plenty of works about good clustering heuristic. Okay.
Maybe the
And,
smallest, the unit bounding.
I don't have a good answer, of course. There are obvious go on, go. One is better than the other, but like to match the two furthest away segments sounds stupid. To match the two closest one, I want to define what is the closest one, but and so on. So so in general, now what will I place at this node over here? Yes, what do I place at this node over here?
5, 6, 7,
Again, remember, every node keeps a bounding box of whatever all its descendants, but it doesn't need to know about it. It just needs to know about the bounding box of its immediate children. So that's what I'll store here. I'll keep the bounding box of its immediate children. Again, how do I match them? $1 million question. Bounding box of the children. I'm done with the yellows. Into the purple, the bounding box of 5, 6, 7, 8 is what I keep at this node. Of course, the node itself doesn't know what is in its subtree. It just needs to know its immediate children, as usual, just what's its own bounding boxes. And finally, at the root, it's a bounding box of the whole data. Height, not much to negotiate here. Log n, nothing to negotiate, log 2 of n. Okay, enough animation. Okay. Okay, what do you have it again? Yeah, and it works as we said in any dimension, any type of shapes. Why do I have these slides again? So let's say part of this slide did not work on. Yeah, you have it once again. Better animation, just didn't remove the previous one. How do I report all the segments that intersect a disk? It's multiplayer video game. I want to know who are the other players at distance 5 miles. So it's robotics parts and it's robotic arms that stands here. I need to know what are the objects that are 5 meters away from my point. How do I do it using the R tree? Same philosophy as always. Start from the root. Is your query disk intersect the bounding box of the root? If not, intersect not necessarily the boundary of the bounding box. Intersect or also include if you are inside, then you intersect the bounding box of the root, and if yes, then branch to the two children with the query. So Q will go to the root, the answer is yes, so it will go to the bounding box of the right subtree, 5, 6, 7, 8, and will go to the bounding box of the left subtree, 1, 2, 3, 4. Bounding box does not intersect Q, so I don't have to visit any of the nodes in this subtree because it doesn't intersect Q. And eventually I'm focusing down on only the objects that hopefully intersect the query disk. Again, think about it as a filtering device. You're hopefully avoiding checking a lot of segments individually. It doesn't necessarily tell you exactly. The only case where you are sure that you intersect the shape is Here is Q. Here is the bounding box, or R of V, and it's fully inside the disk. Then obviously everything in the subtree is inside. Otherwise, you just recurse on both sides. Okay, and it works. Again, check Google to see how many parts. We mentioned graphics, very popular in graphics. You have array. You want to know what are the objects. Sorry. You have array. I want to know what are the objects that this array hits. What the first triangle, the first object in the room, that array coming from my eye to the monitor going through a pixel and then branching forward. What will it hit? I'm asking, does it intersect the bounding box? If yes, then look at which of the two children it intersects, and maybe you prioritize it into the box that first is closer, because if the array hits the box that is closer, you don't need to visit the other box. Now remember, these objects are not necessarily disjoint from each other. These objects are not necessarily well separated, so it's very likely that the two boxes of the leaves overlap each other, as opposed to the quad tree where they're completely disjoint, the left child, right child are disjoint. Here the bounding boxes definitely might overlap with each other. Good heuristic will be you try to minimize it. Right. If my query disk is here somewhere, just a point, and my merging policy was merge together 8 and 1 using one huge bounding box that is almost completely empty, except of the two segments at the endpoint, then you are visiting it in multiple times, never just to discover that it doesn't help you in your search for intersection of the query disk and the segment. Make sense? People are less awake than usual, and I need new markers, so it's a great opportunity. Let's take meet in 5:50.
Yeah. He mentioned it.
No, I was already gonna do that.
Looked at lunch and I was like, this is gonna be odd. What the fuck do that?
And then I talked to Dr. Buzz, and I was like, bro, give me a job, bro.
I know.
Internships, so.
Yeah. Financial. I'm trying to think how to explore.
Sure, OpenAI published their internship stuff.
Did they really? Let's all apply to OpenAI right now.
Yeah, good luck.
Yeah, let's all get projected to OpenAI.
Apply with 300 different emails, hoping for the best.
Yeah, I see that probably. Careers.
It's an advanced career. If they use anything else for others, but I use AI to send for.
Open roles.
Everyone on the internet is a robot except you.
Aren't you just also a robot?
Sometimes I feel like it. We're looking for Trump as new robot.
Ridiculous. So many words.
No shot.
Oh, wow.
400K.
I need to students that are feeling tired and entitled to entitled. They didn't get enough sleep. Two of you can first come, first serve.
That's too much.
One is cold, one not.
I'll take the cold one.
It's too much caffeine. You're be up all night.
God bless.
Stop that, make me jittery. That makes you jittery.
You know what, I'm gonna make it.
You asked about the graphics course and quad trees and R trees and hashing that we saw in the grid. That's also stuff that I'm teaching. They're a bit more practical, a bit, but yeah, a bit less theoretical. The log and I don't see in graphics because that's too theoretical. But quad trees in general, that's definitely something that graphics community likes. Okay, now this slide is slightly anachronistic, but it's still very relevant because you still have hierarchy of memories. Some of your memory works much faster than another, and your SSD, your disk, if you had a hard disk, on your drive, it always works when it takes a lot of time to reach an address, and then you're somehow compensating by reading or writing a big bucket of memory, about a few kilobytes, maybe more, at each iteration. I am waiting for the head of the hard drive to reach to some place, waiting for the hard drive to rotate, but then I will read a big bucket of data, big chunk of data. SSD are less extreme, but it still works much better when you're writing a big chunk of memory or reading a big chunk. Reading is usually faster than writing, but you still want to optimize somehow to say that your CPU works very fast, your main memory works very fast, and then there is a hierarchy of things that works slower but contains more memory. So R3 and the variants of them are star, plus, fits very nicely to this part, the same way that you might have seen B trees that fits into it. That usually what we'll do is R trees, or what people do in graphic geometric databases, is, let's say, I'll use 3, but now the degree of a node will not be 2, like in the R3, will not be 4, like in the quad trees, but will be a few tens or a few hundreds. Which means that when I'm reading a node, I'll read a few hundreds of bounding boxes in internal nodes, and it actually makes my CPU works harder. It's not very efficient for the CPU operation. Just playing with. It's not that nice to the CPU, but it still pays off because what does it do to the height of the tree to keep a degree of hundreds? It means that, let's assume that I have 10 to the 9 many items, or a small number still. Let's assume that that's a number. If it's a binary tree, then the height is about 30, which means that have it all stored in the, again, let's be anachronistic, in the hard drive, it means that I need to go from the root and branch down 30 seek operation until I reach to the leaf that actually contains the data. If the degree is, do I have it here? If the degree is the same number, yeah, if the degree is 1,000, which is still quite feasible, degree of 1,000 of each node, that is, every internal node has 1,000 many children, then and I still have the same number of leaves, the height of the tree is only 3. And a seek operation from SSD as well as works. For hard drive, it means that the whole height of the tree is only 3. And I do have room in my main memory usually for the first root and the first level, so it only boils down to get the leaves, but you don't need more seek operation. So in practice, you actually use to store many nodes in the tree. And you tend to actually, that's in the R plus tree, the same as a B plus versus a B trees. On the leaf, you store the actual data, for a segment, the actual coordinates of the segment, which means that the degree is still high, the number of bounding boxes in the leaf, but now you store the actual data with the leaves themselves. So the degree is larger than 2, but not enormous. What you're storing in internal node is only the bounding boxes that just help you navigate your search left, right. So that's meaning that the degree of internal node is much higher than the degree of the leaf, but the leaf contains the actual data. All in all, meaning that to retrieve one leaf will take only 1 or 2 seek operation in your hard drive SSD. Make sense? And in return, sure, you're a bit more CPU, but it's very marginal, a bit more CPU. But like, you cannot beat binary tree in this aspect, even in the 1D case. But like log 2 of n is a minimum number of log to the base 2 of n is a minimum number of comparison operations that you need to find somebody in a sorted array. So if my height of the tree is log 2 of n, I will not beat it by increasing the degree. I will do more comparison operation, but that's done by the CPU, and CPU is always very fast. Okay, so that's about how R-tree scales to external memory. And by the way, the same will go if your database is distributed. You can think about it, that actually what I need to do to retrieve an item is to ask the server to retrieve the data from it. Again, I'm trying to minimize the number of packages, and in return, every package will be much larger. So that would be in distributed over the web. Yeah. And one more tree before we are moving to dualities, kD-tree. So kD-tree relative to quad tree, but this time I do look at the data and I'll try to decide how to split it into left subtree, right subtree. So quad tree split always start about the original length, and I split so the width of the left equal to the width on the right. Here I'm looking at my data points, and I'm going to build the tree. As before, don't forget, for every node V, R of V is a region of V. And confusion warning, I'm going to store information here in the node of the kD-tree, but it's information that's somehow relevant to the children, or not relevant to RV. It will be clear in a second. So here are my data points. I'm talking about kD-tree. In this case, it's K is 2, so 2D kD-trees. The term is not very informative. That's okay. Look at all the data. Here is R of the root. Usually in the textbook you don't see the original bounding box, but it's very confusing without it, so I added it. In the textbook you wouldn't find this original box. Look at all the data points, find their median. Find their median, split it. Split based on the x. The number of data points on the left equal to the number of data points on the right. Plus minus 1. And now I look at all the data points on the left, count how many, pick the median, but now the median based on the y value, not on the x. And I split, and similarly on the right, and I split in the median. And there is no reason to think that the two medians will be in the same y coordinate. It might be, but it's accidental. So versus the 4 quads of the quadrant. Okay, and now next I'm back to splitting by x. So out of all the nodes in this quadrant, split by x at the median. So I have 3 points here, 2 points here, almost equal. 4 and 5 almost equal, and so on. And keep on going until you end up where every node V has only one data point in its region. So what will be the quad tree, the KD tree that I'm going to build? I'm going to split it into, I know what is the overall region. What I store in the root, I can store the region of the root, which is the whole world, but more important, I will store in the root what is the first line that I use to split. And actually I know that this line will be vertical because I know what I start with x, y, x, y. So first line will be the first line that I split. So it's L1 here, denote this line L1, but remember, it will only affect looking at the children, not the region of the root itself. What do I store in the left subtree? L2, split along the y. L3, split along the y. L4, split along the x once again, and so on. And now for the region of L4, the region of this node that stores L4, that's a bit convoluted. The region of L4 are A and B, and the split between them is based on L4. So let's go this, not L4. Okay. And if it's 3 dimensions, then I'll split by x, split by y, split by z, x, y, z, x, y, z. Alternate by the levels. And so on for the d dimension. Okay, so everybody understands what it is. And eventually I'm down with regions that are just contain one data point, and as usual I need to store that exact data point somewhere because I needs to know what is its exact xy. So that's what I stored in the leaves. Yeah?
So basically in the last level you just store the data point instead of those levels, right?
In the
last, in the fourth?
Yes, so yeah, so here I'm saying I don't need to split anymore because it's a single point. So that's what I store. So I'll just store the actual xy coordinates or pointer to in the array of all the points, like in the DCL. We've seen this. Yeah.
What if all of the points are in a super dense region of the 2D graph that we're given? Like, maybe they're all in some very, very small corner. All of the points are super dense.
I split in the median. Here I will split. I count how many points. Let's go back to L1. I count how many points I have, sort them based on x, take the one with index n½ If they're all in the left, it means that the median would be probably way to the left. That's exactly what it's quad tree versus kD-tree. It's sensitive to the data, of course. So median meaning you should start by sorting them all by x, similarly sort them all by y, and then each time you are just once you separate, you're just putting everybody from the sorted list, everybody to the left, everybody to the right, and keep picking the medians at each iteration.
Well, every number line is continuous, so you can always break it separate to half. So, but I mean, the only case is like if you have collinear points, but then because you're splitting by x-axis and y-axis, you're still gonna be able to
yes,
split them.
yeah. If they are horizontal, then I'm in trouble. Then the y-axis. I should assume that they could be collinear, but at least not all be horizontal nor vertical. And you see why I do want to alternate between the x and y, because like in this example, if I'm only splitting by x, it would mean that my leaves, each leaf will correspond to some extremely narrow part had I not do this alternation between the x and y. So actually you can use kD-tree quite efficiently to find nearest neighbor, if you want, even in higher dimension. It doesn't come with exact bound on the running time, but you can definitely find what is a leaf that is closest to me, what's a point there, who is still, there are various algorithms that can take the kD-tree and applicable and works very well to find nearest neighbor. Quite popular. But so is quadtree. Okay, running time. If you keep the two lists sorted, then there is a recursion formula. If you like recursion formulas, I don't. It's like recursion formula for endpoints. What are you doing? You're spending order n time. You start by sort by x, sort by y, sort by z. Then you're spending linear time to just separate them into left and right in each, but you still keep the sorted parts in each list, plus 2 times running time of each set. But now I am sure that each set has n-half many points, and it's constant time when they start, altogether n log n for the whole thing.
Couldn't I use these trees for approximation, data approximation as well? It's like, so that, you know, if I could just, like all the points in the nearby neighborhood can just be condensed into one object.
Excellent question. We'll talk about something called a well-separated pair decomposition. That actually quadtrees are a bit better for it, but it exactly looks at a set of points and find partition of pairs. Like I'll say, I'll start with a quadtree actually, and now you'll give me some number. It's an excellent question, and we will get to it in the course, but actually you'll tell me that you want 3 WSPD, well separated pair decomposition. And now what will I do? I'll give you list of pairs of nodes in the quadtree, and actually only n log n many nodes, so it's pretty cool, they're pretty compressed. With the property you ask for 3, that's great. So now what do I do? The diameter of each such pair, 10 and say 10, it means that the distance between them, if that's the radius of each ball, then the distance between these balls is at least 30. So this is a cluster, and this is a cluster. And what do I do with all the points inside the cluster? The same thing recursively. So, and I'll report all such pairs, all such different clusters at the same time. So yeah, it's this data structure, like possibly there is a version of it in the, yeah, I don't know to say about kD-tree and clustering, but of course clustering in nearest neighbor is very based there, and kD-tree will help it. I want to speak about, we have time to talk about how do I answer counting queries. Counting in quadtrees, just to remind you, I have a region. I want to report how many points do I have inside the query region. And what do? I store for every node. We saw it, every node V stored this size of V dot size. How many points do I have in the subtree? And the moment that a region like so, my query contains R of V, I just add how many points are there in R of V. R of V could be a leaf, but more efficiently if the whole region is inside R. a whole subtree, the whole tree, is inside my query region, so I don't need to recurse on the children of it. I just return the counter. So what do I do with kD-tree to answer reporting question? Exactly the same trick. It's also hierarchical data structure, and once again, every node V has its own region, ROV. Let's keep this counter, the size field over here. So I have 8 data points. The root will store, I have 8 inside. I have 4 data points on this subtree, A, B, C, D. That's what I stored over here. And now, when you have a region, if the region is full inside, I thought I have an euro. Yeah, here's a better slide of the same thing. So, you have a query region. You have the region ROV. How do I know ROV? I can still do it by computing the path to the node, but there is no more anymore the nice partitions except in the middle. Instead, you're saying, if I branch to the left, then instead of the whole region that I started with, it's a whole region intersection with one plane, and to the left of this, one plane, half plane that is vertical. And I might be in the intersection with half plane that is horizontal, half plane below me, half plane above me, but I'm always inside a rectangle. So it's always what is the lowest break based on the path. I'll let you figure out the details. And now, to answer the reporting, once again, I have the 3 cases that I had in the quad tree. I'm at a node V, ROV, its region, is completely outside Q. Then return 0 if ROV is disjoint of U. If ROV is fully inside Q, ROV is fully inside Q, return how many nodes do you have here, and then you're adding it to the overall count. And if ROV partially overlap Q, the only leftover case that you have, so it's not the only leftover case, but one of the overall cases, then you need to recurse on, check how many you have on the left subtree, how many you have on the right subtree in the figure of quad tree. That's basically it. The only case that I didn't mention is that if V is a leaf, then it might or might not include D over here. I cannot decide. So unless ROV contains it, that if ROV if the Q intersects this region, then I need to check is the point D personally is inside the disk or not. So that's the same mechanism that we saw in the quad tree. The same mechanism, by the way, that we kept rank by. That was a mechanism that you have in homework 2 for maintaining the rank. But so example, here is the query disk, a query rectangle. So in practice, it's much nicer to answer such queries if the query is a rectangle rather than a disk. What do? I go to the root, ask, hey root, your region intersects the query region? Yes. Fully contained inside the query region? No. The root is not there, so I have to branch to the 2 sides, from which everything to the left is inside my query region. So I'll just return that this query region 4 will answer 4, plus you also need to go to the right. Right, you intersect with everything to the right of L1, which brings you over here, from which you intersect both children. You visit these 2, from which, with respect to L7, just go to the left of L7 and check personally, and go to the left of L1 and check personally over here. So that's your search. And of course, it might be more than logarithmic, but can be bounded. Well, yes. In practice, it works very nicely. And the bound is a bit pessimistic, but before I prove the bound, I want to convince you that we visit the children of a node V if and only if the boundary of Q, the boundary of the query region, intersect R of V. Here is R of V. Here is a boundary. Here is Q. Of course, no intersection over here. Now, do I visit V in this case? Yes. Do I visit the children of V in this case? No. But no, so it satisfies my claim. The boundary of Q, this blue circle, does not intersect R of V itself. The disk intersects, but not the boundary of the disk. So I just return the count over here, but I don't need to visit the children of V in this case. What about this case? In this case, I'm neither here nor here. So in this case, I do need to visit the children of V because I cannot decide inside or outside. So the little theorem that we'll prove next meeting will say that every such query, as long as it's all rectangles in a query disk, will visit hopefully much less, but in the worst case, it will visit square root n many nodes of the tree. So out of all the tree has n many data points, but only square root of them will be visited. In practice, of course, it's much less than this one. Thanks, see you. And once again, the homework, yes, is until Thursday, at least.
I kind of remember the compressed tree kind of looked like how Hoffman compression It's been a long time, I couldn't remember. I implemented that.
Ben, you want to meet up tomorrow?
Yes.
What time?
Sure, tomorrow.
But every time you have a thread, a long thread, you encode it into a dictionary and show the tree.
Right, but we don't see immediately.
Maybe
I
I don't
can,
know
yeah,
the details.
but
Yeah.
no.
But I would think some data compression uses that technique.
Where I'm also sometimes showing it is that there is data structure called tries, T-R-I-E, and that's similar. It's just like quadtree, but it works on strings rather than on. And then you have a similar thing.
Yeah. When I was writing video games so long ago, I had to be creative. I made up a lot of these trees by myself, kind of, nothing to teach me. Still sounds familiar.
I just want to know what your favorite flavor is. I just want to know what your favorite flavor is.
You wanted to?
Know your favorite flavor.
No. Don't worry about it. I have the subscription on Amazon. Seriously, I get all yours.
Thank you very much. Have a great day.
Do you have time for a quick
By the way,
question?
this all shouldn't be in the
So you
crate.
said
Work.
Shouldn't be in the crate. So you said when we have a shape like this and our medial axis is like that, right?
Mm-hmm.
When it goes to here, the local feature size is 0, right? So, is it even possible to fulfill the crust requirement then, that the local feature size?
No. The crust will assume that no, because it will mean that I have a geometric sequence of data points that is going to infinity if I want to do it.
So you need
infinite points. Need actually to have epsilon 1, epsilon 2. And epsilon 1 will say, and epsilon 2 will say if I'm z close distance, absolute distance of epsilon 2, then no guarantee. I'll be close enough and my shape hopefully will be. So I need some absolute number, integers. And basically if I want to reliably reconstruct sharp edges, it's a very different topper. So no, but definitely not a crust as is. No.
Yeah.
Like there is no way that no way, but it will not be unless I sampled right here.
Mm-hmm.
There is no way that this will be a Delanoy edge.
Yeah. Okay.
So yeah, so I'll be happy to tell you more about it. I need to finish.
Yeah.
But yeah, as far as the class concerned, crust will not work as is. That's a requirement.
Is it okay if I ask how we're supposed to determine how many points would be needed for the triangle then? Like, unless I'm understanding how the medial axis works wrong.
Oh, no. As a question?
Yeah.
You just tell me
Like,
what
it
the
would be
answer.
infinitely many points then, right?
It asks
Yes.
for points on the boundary, so I counted the vertices as on the boundaries, so you kind of have to go reach the vertex, right? Or
If the answer is, I don't want to commit. If the answer is infinity, then say it's infinity, and that the crust is not applicable for this point, and it's kind of a tricky question,
Yeah.
maybe unfair. But
Okay, that makes more sense.
I think, yeah.
Thank you.
Is it? Sure.
I have more of like a logistical question. So at the end of class last week, when we were asking about homework 2, you had said that there would be like a day extension when I was here. And so I went to go turn it in because I wanted to look at it.
So submit it today.
So I tried, but Grace
I'll ask,
doesn't work.
yeah,
And I sent
let's
you
do
an
it right now because
email.
we will go to my office weekend. I'll tell Amir, I'll tell Amir that there is more submissions and.
Okay.
Okay, I'll add another day to homework too, so it should be.
And I just wanted to double check. This is your email, right?
Yes.
Okay, perfect. Yeah.
So, my apology.
Oh no! I can only imagine all the stuff that you have to go through with all this. So.
yeah, I know it's a bit early in the, I don't know, maybe it's a bit early because
Yes, I
we've
can watch.
been in the semester. Yeah.
Yeah, no problem. I know how you participate. That's what I consider about. Where are you applying to?
Columbia, Berkeley. I'm looking more into like machine learning. Yeah.
It will not be as strong as somebody that supervised you in a project.
Yeah.
If one of the machine learning, but I'll say you were in class, you are very aware of what's going on in the class. You are one of the top 3, 4, 5 students. That I'm happy to say.
Yeah.
Presuming, wait. If your grades are, I don't know about your personally. Assuming that you got an A and your grades are all A, usually it's not enough for me to write a letter because it's nothing personal. In your case, if your grades are decent, and then I'll be happy to say your grades are putting you at the top, but grades by themselves, people can cheat or can get grades in. That you personally participated extremely well in the classroom, which I definitely am aware of.
Yeah, thank you. Yeah. It's just because they asked for I think 3 letters, so I'm just asking like 3 different professors, and you're one of them I consider.
I'll be happy, but as far as top 10, you probably need somebody that works with you, and if you have publications, that will be great, even for master. But yes.
I'm working with Dr. Tao. He's right here on the 7th floor too. I think his office is on that side right here. Yeah. I'm working with him right now, so I'm also probably gonna ask him about that as well.
I think that he's mostly work with his MIT group, if I remember right.
Yeah.
If I'm remembering, so if his advisor is involved in any way with your work, that can be, it will carry much more weight if somebody at his, because letter from MIT will carry more weight, but he's extremely good. Like, I know his record. So it's all good, and I'll be happy to help whatever.
Alright, yeah, thank you so much.
Sure.
Alright, thank you.